So this is going to be the first lecture on digital design. So I'll introduce you to the digital system as such today. So what is an analog system? Let's first try and define what a digital system is. Analog system in which the physical quantities of signals may vary continuously over a specified range. That means the value of the signal in an analog system can be infinite, right? Suppose it's a sinusoidal signal. Okay, what we see, what we hear, they are all, when I am speaking, if you are hearing it directly, not through an internet line, then if I am speaking something, if you are listening to it directly, then it's an analog signal, because my amplitude can take any values. Okay, the amplitude values can be anything. Okay, so that is the reason we call it as analog system. Okay, similarly the colors what you see, the temperature what you sense. Okay, it can be the temperature, room temperature could be 27.0001 or it could be 27.01. Okay, anything. So that is known as an analog signal. It can have infinite number of values. Okay. Okay, there is a question, is there any issue to install that application in office laptops? No, it is not. It's a free software which is available on the net. So I don't think there is any issue with that. If there is any issue at your end, please let me know. Okay, it is an LT Spice. It's a free software which is can be downloadable. So there is no license issue there. So you can do that. In case there is an issue, please let me know. Okay. Then if there is an issue, we'll find some alternate means to that. Okay. So now, so this is an analog signal which we said it can have infinite number of values. Okay. Now a digital signal means it can have only finite number of values. Okay. So for example, suppose the voltage level is from 0 to 16. I can have only 16 different unique values. Okay, so if it is 16 different unique values, the voltage can be either 0, 1, 2, 3, 4 up to say 16. Then I can call it as a digital system, right? So in this, if you have to represent one information here, since it can take any of the 16 values, so it will be an 4-bit system. That is, and if I have to encode this into a binary digital system, then I will require an 4-bit system, like 2 to the power of 4 is 16, right? So each of these, like this can be 0000, this can be 0001, so this can be 0010, so on and so forth. So these are 16 different unique digital values. Okay, and since there are 16 values, so you require an 4-bit to represent each of these different values. Suppose I have I have an 8-bit system, then this 16 this voltage level 0 to 16 can be divided into 2 to the power of 8 is 256. So I can divide it into 256 levels, so it will be more accurate. So henceforth, so if you keep increasing the number of bits, the same analog range can be divided into more number of levels, so it will become more accurate. Is it understood by everybody? Okay, so this is what a digital system stands for. Yeah. Okay. Now we have binary system. Okay, in binary system, okay, this is where this forms the basis of all today's digital system. Although ternary logic is slowly coming, is in the research state, and some microprocessors based on ternary logic has been already implemented, but then binary system is the one which we are going to focus in this course. Okay, so in the binary system, they can be two logic states, 0 and 1. That means the voltage levels and can be either 0, logic 0 or logic 1. Okay, logic 1 doesn't mean voltage 1. Okay, these are two different logic levels represented by a low voltage and a high voltage. Okay, so for depending on the various family of gates, these voltage levels will change. For example, in TTL gates, the logic 0 is 0 and the logic 1 is 5 volt. Okay. For a CMOS technology, for your ICs and all which you have, for 180 nanometer technology, when I say 180 nanometer technology, we will study about CMOS also subsequently in the class. The channel length is 180 nanometer, in which the logic 0 means 0 voltage is 0 and logic 1 is 1.8 volt. So, as you keep increasing the technology, like for 45 nanometer technology, logic 0 is 0 and logic 1 is 1 volt. For CMOS 7 nanometer, logic 0 is 0 and logic 1 is 0.8 volt. Okay. So, this logic 0 and 1 will change depending on the logic family which we are talking about. Okay. So, for the lab purpose, we are going to use TTL gates. So, logic 0 will be 0 in and logic 1 will be 5 volt. Okay. So, when we are doing the simulation in LT Spice, ensure that whatever voltages we are giving, for logic 0 we need to give 0, for logic 1 we need to give 5 volt. Now, let us see what are the advantages of digital system. Okay, why are we all giving so much of importance to digital system? Okay, because everything in this world is analog, right? What we speak is analog, what we see, what we feel, everything is analog. But then why are we talking so much about a digital system? Okay, the first and foremost is when we are transmitting an analog signal from say place A to place B. Okay, so as long as it is like if I am sensing a temperature and sitting in the room, it doesn't matter. Okay, you can have an analog system. If I am speaking to you directly in a hall, it is an analog system. So I can just amplify my analog signal, and if it's a big hall, and I can just amplify it through a mic and a speaker. Okay, but whenever I am transmitting a signal from place A to over a large distance, so these signals get transmitted either through an RF channel or a wire channel and all. So a lot of noise gets introduced into the system, into the signal while it is being transmitted. At the receiving end, I have to amplify the signal, right? So because it gets attenuated by the time it reaches the receiver, and then once I amplify it, the entire noise also gets amplified. Okay, so that is it can cause a lot of inconvenience to and errors. So in a digital system, you are transmitting only zeros and ones. Okay, so they will pick up some noise while being transmitted, like in the analog signal they will pick. But at the receiver end, I can keep a threshold. Like suppose I am transmitting 0 and 5 volt. Okay, when I receive these signals here, if I can set a threshold of 2.5 volts. So if the signal which is received is below 2.5, I can say it is 0, and if it is above 2.5, I can say it is 1. Right, so the noise can be eliminated. So it doesn't matter if there is some noise. If this signal is instead of if this signal is varying between say 3 to 6 volt because of noise, it doesn't matter. As long as it is above 2.5 volt, I am going to set it as 1. So all those noise which has got into the system because of the transmission channel, so that gets eliminated. So that is one of the big advantage in the digital system. Okay, so that is why it is very clear. If you have ever listened to radios and all, in not the FM radios, in the SW radios, like you have shortwave radios and all, you will find there is lot of noise there. Okay, that is because they are all based in the they all use analog modulation techniques. Okay, and they are analog signals. Okay, but whereas today whatever you hear in your computer through your net and all, so they are very clear because they are all transmitted in the digital format. So there are other great advantages also in digital system. Computation is easy because all the microprocessors and digital systems, they are use binary logics. So it is easy in binary logic to add data, multiply data or manipulate data. So and do various complex logical operations and arithmetical operations. It is pretty easy in the digital domain. So all microprocessors are based on digital system. So that is why digital system is more advantageous than the analog system. Okay. Similarly, storage and retrieval of data is easy. So whether it is be RAM, hard disk and all, you can easily store a digital data. Okay, analog data, you will require that particular storage element. It has to capture infinite number of values. It should be able to read infinite. If it's an analog signal, it has to read infinite number of levels of analog signal and store it, and then subsequently we should be able to read it. Whereas in digital storage domain, the memory element has to capture whether it is 0 or 1. That's all, only 2 levels. And then while reading also, you just have to read either it is a 0 or 1. So storage and retrieval of data is pretty easy. Okay, so that is one. And then error detection and correction is possible. Okay, that is also possible in a digital system. Suppose I am sending an 8-bit data. Okay, I can have one additional bit, 9th bit, known as an error bit. Okay, a parity bit. Okay, what does the parity bit do? So if there are total number of bits, ones in the 8-bit data is odd, I can set the parity bit as say 1. Okay, and if it is total number of ones is 0, I can is even, I can set it as 0, the parity bit. Okay, so the parity bit will essentially be such that, so that like if I repeat it, if say the number of ones is odd in the 8-bit total, if it is say 00001, then the parity bit will be 1. If it is 00011, that means total in the 8-bit there are 2 ones, then I will set the parity bit as 0. Okay, so the once I receive in the end, okay, I will check, okay, from the parity bit, if I have whatever I have received is correct or not. Suppose the parity bit is 0 and I have odd number of ones, so that means while transmission some error has occurred. So that way I will be able to detect the errors. Okay, so instead of one parity bit, I can have two or three more bits, which is known as the error correction bits. I'll be also able to correct the errors, okay, after receiving it. Okay, so that we will learn subsequently. So error detection and correction is possible in a digital system. Okay. So, and digital signal processing enables a wide range of. So, digital signal these days you have DSP processors which can do a lot of image processing and signal processing. Okay, so that is the reason why digital systems are beneficial. Data encrypting and de-encrypting is also very secure. Suppose I have a digital data which is being transmitted, say between Kishan and me. Okay, Kishan has got an 8-bit data. What he will do is, in his receiver, he will mix up that data with some pseudo-random series. What is pseudo-random series? It might appear random, but it is not actually random. Suppose it is a random series like 0011 0011. Then 111, something like that. It appears like a random signal. Okay, he is going to mix his digital stream with that particular series. It could be a 16-bit series. Again, he will keep repeating that 16-bit series, and he will keep mixing it with the data which he is transmitting. At the receiving end, I know the code with which the sequence, pseudo random sequence Kishan is mixing. So if I know that what is the kind of sequence he is using, I can use the same sequence and decode the data. Okay, so he, like for a third person, if for example Shweta is trying to intercept that, she will not be able to decode it as long as that code is not available to her. Okay, so that is the reason data encrypting. That's what this WhatsApp and all these softwares they do. Okay, they end-to-end encryption it means. Okay, so that only that code through which the data is getting encrypted will be known only to the transmitter and the receiver, and they will use that code to decode it. So this is very secure method of doing it, and it is possible only in digital system. So these are all the advantages of having a digital system. Okay. Now there is another advantage of a digital system is time division multiplexing. So because if you see the frequency spectrum available for communication will be limited. Okay. So if you see here, if I come back here, you will see in a digital system you are not continuously transmitting data, you are sampling the data and sending it at say t is equal to 1 nanosecond and t is equal to 5 nanosecond, 10 nanosecond. So you are spacing it out. So in between there is space. Okay. So in this time duration, some other channel also can transmit using the same bandwidth. Okay. So that is known as time division multiplexing. So in the same channel, n number of users can be multiplexed. So at this time this channel is transmitting, at some other time some other the next channel 2 is transmitting, or if you have then channel 3, channel 4, like you can have multiple subscribers being served by a single transceiver. If I speak in terms of a mobile tower using the same frequency, multiple subscribers, they can all be sampled at different, they can be allotted with different times. Okay, so that is another advantage of having a digital system, right? Now every good thing will have some drawbacks also. So even in the digital system we have some issues. So the first one is it occupies large bandwidth. When I say a square wave, okay, what is a square wave? If you have learnt Fourier series in mathematics, okay, if square wave is actually sum of many sine waves. Okay, so say if it is a 1 kilohertz square wave, it is actually 1 kilohertz sine wave plus 2 kilohertz sine wave plus 3 kilohertz of sine wave till infinity, and the amplitude will differ. Okay, that means if it is a 1 kilohertz sine square wave, 1 kilohertz sine wave magnitude will be the highest, then 2 kilohertz sine wave will have little bit lesser amplitude, then 3 kilohertz will have 4 kilohertz. It will be in harmonics, like 4 kilohertz, 1 2, if it is 1 kilohertz, then 1 2 3 4 like that. So if it is 2 kilohertz, 2 4 6 8 like that, it will be multiple harmonics. Okay, so all these harmonic components will have lesser of magnitude. So the first few harmonics will have a large amplitude. So it is actually a summation of many signals which will give an square wave. Okay, so that's why digital systems will have a large bandwidth. Okay, so generally in a channel, when you transmit a digital signal, if you are going to transmit a digital signal, you will not have infinite bandwidth. You will band restrict it to say you will give, if it is say 1 megahertz in a digital signal which is being transmitted, you will take say 10 megahertz of bandwidth. So the first 10 components and frequency components will get transmitted. So you will get these kind of waveforms here. It will not be pure square wave at the receiver end. But then, like I said, you can filter it out. You can set a threshold voltage, and if the voltage is above certain threshold, you can take it as a 1, and if it is below certain threshold, it can take it as 0. So this kind of waveforms, distorted waveforms, this distorted waveform is because of the channel bandwidth being restricted. So that distortion can be eliminated by using a filter which will make a decision whether it is 0 or 1 depending on whether the signal is above a certain threshold or below a certain threshold. So this is the disadvantage of an digital system. The second disadvantage is almost everything in the real world is analog, whether it is temperature, what you see, what you smell, okay, what you speak, what you hear, everything is an analog. So obviously when I want a digital system, there will be analog to digital conversion requirements and also digital to analog conversion. Okay, so ADCs and DACs will be required. Okay, and also for long distance transmission by wire, okay, it is generally done by RF signal. You can't transmit 0 and 1s as a DC signals. Okay, so they will get attenuated badly. So that is why we use an RF signals. So when we use RF signals, the digital signals have to be modulated with an analog signal. So these are some of the disadvantages while using digital system. Yeah, am I audible? Is there an issue, Kishan? Anybody? Yeah. Okay. 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 So let me just introduce you. This I am just introducing you right in the beginning itself, some basic binary logic circuits, because you will require these gates to do your lab assignment. Okay, so the first gate, which in a digital system is known as an S gate, or you can call it as a buffer. Okay, so input is 0, output is 0, input is 1, output is 1. Then what is the great fun in having this? Because generally we use these kind of gates if you don't want to load the previous stage. Suppose it's a microprocessor. Okay, you take the output of a microprocessor and you are going to drive, say, a memory. Okay, so the memory will be placed somewhere other on the PCB. So there will be some wire which will be running onto the PCB. So there will be a huge capacitance and which will be there. So you don't want to load the microprocessor, so you use a buffer in between. Okay, buffer basically what it does is it will have an higher driving capacity than the input, and it will isolate the input and the output. Okay, so that is the reason we use buffers. Okay, so the symbol of the buffer is just like this. It's just a simple triangle. Whatever is input is available, that the same thing will be available in the output. But what it essentially does is it isolates the input and the output, and it will have a higher driving capacity if to drive high loads. Okay, then we have something known as the NOT gate. Okay, so what a NOT gate does is it just inverts. If the input is 0, the output will be 1, and if input is 1, the output will be 0. For an if I say in terms of TTL gate, if the input is 0, output I will get as 5 volts, and if the input is 5 volts, I will get output as 0 volt. Okay, so if it is CMOS 180 nanometer which works on 1.8 volt, if it input is 0 volt, output I will get 1.8 volt, and if input is 1.8 volt, I will get it output as 0 volt. So it will just invert the logic. Okay, so now the voltages depends on the family of the gates which we are using. Okay, so similarly I have something known as an AND gate. Okay, so the AND gate is 0. AND means this and this. Okay, if both are 1, then I will have output. If that is why it is known as AND gate. Okay, this is also 1, this is also 1. Both the inputs A and B are inputs are 1, then the output will be 1. If any one of them is 0, then the output will be 0. So this is known as an AND gate. Similarly, OR gate. OR gate means either this or this. One of them is 1. Then the output will be 1. So if you see here, for 0 0 it is 0, for all other input output and input combinations the output is 1. So this is known as an OR gate. Okay, similarly I can have an XOR gate. And what's an XOR gate? So the XOR gate and exclusively OR, that means if both are 1, then it will be 0. Only when one of them is 1, the output will be 1. So this is known as an XOR gate. Okay, so from the transistor level point of view, okay, so AND gate and NOR gate cannot be implemented directly with a transistor. we will have to implement a NAND gate and then put an inverter, and NOR gate and put an inverter. And what is NAND and NOR? I will explain you just. OR gate can be directly implemented as it is with a transistor. Okay, this is what a NAND gate I was speaking about. Not AND. Not AND means it is inverted of AND. So for an AND, what did we have? We had 1 1, it was 1. For all other combinations, it was 0. So if you see this small round which is placed here, so the symbol from here, there is no small, so this is the symbol for the AND. So not AND means this small bubble. This small bubble generally in digital circuits means it is getting inverted. So this becomes an NAND gate. So for 0 0 you will have 1. So for 1 1 you have 0. For all other combinations it is 1. Similarly a NOR gate. Okay, NOR gate also it's an OR gate. If you see, this is OR gate, and then you are putting a small bubble here. So this is 0 and these are all 1 for NOR gate. Here it will become neither this nor this, nor you can call it neither this nor this. So this becomes 1. All are becoming 0 here. Okay, so these two gates are generally known as universal gates. Okay, now why do I call it as universal gates? Is any digital function can be implemented using NAND gates. Okay, so we will see that whenever we define any function, it could be a plus b plus c into d into f, whatever. So the entire function can be implemented only using NAND gates, and you can't implement only using AND gates, because a plus b into c, okay, so those kind of things cannot be implemented by using only AND gates. But with NAND gate you can implement the entire function. So that is why it is known as universal gate. Similarly, those Boolean expressions can also be implemented only using NOR gates also. Okay, so these two gates are hence known as universal gates. Also, when I speak and if we try to implement in transistors, with transistors, I can implement NAND and NOR gates using transistors. I cannot implement an AND with transistors. What if I have to implement an AND with transistors? I have to implement NAND, and then I have to put one NOT gate. NOT also I can implement this NOT also I can implement using transistors. So I will have to implement a AND and then implement an NOT, and then put them in series to get, I have to implement a NAND and then put a NOT in series, and then to implement an AND circuit. Okay, so this NAND and NOR are universal. Okay, so that is about an basic binary logic gates. Now we will see, just this is for history, how the digital technology has evolved. So the first digital family is known as diode transistor logic in 1959. So it used as a few diodes and transistors to implement a basic gate, and using those basic gates higher circuits were designed. So this basic NAND gate or NOR gate, how it got implemented with diode transistor logic, that we will see in subsequent classes. Okay, so there were certain drawbacks in that. Then they came up with resistor transistor logic in 1965. This is slightly, this performance of this gate was slightly better than that. Okay, after that the TTL logic, which is known as the transistor transistor logic, that was came into use in 1963. Okay, now this is still available, this transistor logic, for discrete IC. Okay, so these kind of ICs for 74 series ICs you will have. Okay, they work on TTL logic, which uses a 5 volt power supply. This is still available. So at PCB level, wherever you don't have to see, if it's a small circuit, you don't have to use the entire microprocessor for that. Okay, so small digital circuits can be implemented using discrete ICs, like a set of ICs. You will have AND, adders, subtractors, various storage units, all based on TTL ICs like this. So they are known as the discrete ICs. Okay, it is not a microprocessor, but small functional blocks are available. So if the circuit is not very complicated, you can, instead of having a microprocessor, these ICs, they cost only this IC will cost only 20 rupees or something. Okay, so if you have to implement a small say an Equis system, or in your house also certain switches are there for certain combinations of switches. You want to switch on the AC, say if the temperature is below a certain value, or only when the commercial supply is there. So if the set of conditions is limited and the set of outputs is limited and the computation is not that difficult, instead of having a full-fledged microprocessor, you can implement things using discrete ICs. Okay, because they are very cheap, and it doesn't require a lot of power. So in a small PCB, you can implement such functions. So these are still available. So that is the reason the entire lab is designed using 7/4 series TTL chips. Okay, now after that came the emitter coupled logic. Okay, these 4 logics, they are all based on bipolar junction transistors, that is BJT. Okay, so the first microprocessor 360, this is from Intel, which use the emitter coupled logic. Okay, then you had 460, 560, and then you had that Pentium series coming in, then core 1, core 2, it started off like that. Okay, so that is how, this is the one of the first Intel microprocessor 360. Okay, and then subsequently in 1974 then the CMOS technology took over. Okay, so we'll learn about these later on. The CMOS technology, the basic advantage is it is fast, it occupies lesser space, and it consumes lesser power. Okay, so the first chip had 2000 transistors on it, and the device dimension was 10 micrometer. As on today, AMD has got 7 nanometer chips. Okay, that means the channel length is just 7 nanometer. So you have billions of transistors in the AMD microprocessor. Okay, in one chip. So Intel is still struggling to, I think 2023 they will come up with 7 nanometer. Presently their chips are 14 nanometer. So this is how the technology has evolved, and digital technology has evolved over the years. Okay, now I have something known as noise margin. Now we will see some common technologies of digital system. Okay, so you have something known as a noise margin. Okay, what is a noise margin? See, this is an for a 7/4 series. Okay, this is one IC which is driving the second IC. Okay, so no, suppose this is the input which is available, this is the output from the of the IC. Okay, now input, if the voltage is between 0 to 8.8, it will take it as logic 1, logic 0. Okay, if the input is between 0.8 to 2 volt, okay, then the IC it may not be taken as 0 or 1. It is forbidden. If you give a signal to a TTL gate, any voltage between 0.8 to 2 volt, okay, so it can take it either as 0 or 1. So we can't be very sure, it won't work. So that's why we should not be giving any input voltage between 0.8 to 2 volt. Now, any voltage above 2 volt up to 5 volt which is given to the IC 7/4 series IC, it will take it as logic 1. Okay, so let me repeat it once again. Okay, any voltage between 0 to 0.8 volt which is given to an 7/4 series IC, it will take it as 0. Okay, so not necessarily I give 0 volt, because if there is some noise in the signal, that noise can go up to 0.8 volt also, doesn't matter. It will take it as logic 0. It will take it as logic 0. Okay, similarly any voltage above 2 volt if I give, it will take it as logic 1. So I don't have to give 5 volt. So even if this voltage drops up till 2 volt, doesn't matter, it will take it as 2 volt. And these TTL gates, okay, at the output, okay, for a logic 0, so one IC can give any output voltage from 0 to 0.4 volt maximum. Okay, So depending on IC to IC, there could be some defects in the fabrication process. So there has to be some tolerance. So this output voltage can vary from 0 to 0.4 volt. Okay. Similarly, the output, not necessarily it will be 5 volt, it can be anything between 5 volt to 2.5 volt, the output voltage from this IC. Okay. So these are the output ranges, these are the input ranges. Now if you see here, if my 0.4 volt is the output voltage, maximum it can come here, right? And in the next stage, if this is going to drive one more IC, in the next stage up till 0.8 volt, and it will take it as 0. So what is the maximum noise which can get introduced into the system when I am transmitting this logic 0? This will be 0.4. 0.8 minus 0.4 volt is 0.4 volt. So this is known as noise margin low. That means the maximum value of 0 which I am going to transmit and can be 0.4, not necessarily 0.4, maximum value can be 0.4. And in the next stage, the maximum value for which it will be considered as 0, okay, is 0.8. Okay, so this difference, so what is the maximum noise which can get introduced? 0.8 minus 0.4, it is 0.4 volt. Okay, so this is known as noise margin low. Excuse me. Similarly, when I am transmitting an output voltage, the minimum voltage which I would transmit for one is 2.4, whereas in the receiving stage up till 2 volt, it will be considering it as 1. So what is the maximum noise which can get introduced into the system? Minus 0.5 volt. Like this 2.4, because of noise, it can fall down up to 2 volt. If it is falling below 2 volt, then the next stage will not be able to recognize it as logic 1. So what is the maximum noise margin high? Okay, that is known as noise margin high. That is again 2.4 minus 2, that is 0.4. So for a TTL gate, this is known as the noise margin. Okay, so these are some of the common terminologies used in digital system which you should know. Okay, and then this is something known as propagation delay. So this is the input signal which is given. So this is for an inverter. So if it is 0, the output should be high. If it is 1, the output should be low. When this input signal is going from 0 to 1, the output will fall from 1 to 0. So at this instance, at T0, the input is transiting this 50% point from 0 to 1. The output is coming to the 50% at T1. So this time duration is known as propagation delay, high to low. Okay. Similarly, when the output signal is going, input signal is going from high to low, the output signal will go from 0 to high, right? And then at this instance, it is falling to 0. This 50% point is T2, whereas the output signal is going to high at T3 instance. So this distance, okay, this time duration is known as transmission delay low to high. So for each IC, it is not that it will have 0, there will be some finite propagation delay. Okay, so there will be some time required for the output to get stabilized. So that is known as propagation delay. So you should know all the limitations of the system when you are designing a system. Okay. Similarly, there is something known as a rise time and fall time. Okay, the fall time is when the output is falling from high to low. So from 90% of the value to 10% time. Okay, when the signal is falling. So this time duration is known as fall time. Similarly, when the signal is going up from 0 to high, from 10% to 90%, whatever is the time duration, so that will be known as the rise time. Okay. With this we come to the end of lecture 1. So in each contact sessions we are going to have 2 lectures. So we have come to an end of first lecture. In the next lecture we are going to have I am going to introduce you to number systems.